Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In last few lectures we have been discussing the problem of harmonic oscillator. Just to make a recap of what we have discussed so far, we would start today's lecture by reminding you that we started with the point that we had the Hamiltonian of the harmonic oscillator, which we wrote as sum of the kinetic energy operator plus the potential energy operator. If you remember, while discussing the solution of this Hamiltonian, instead of solving this problem in terms of position and momentum operator, we expressed this Hamiltonian in terms of a creation and annihilation operator, where A plus and A minus operators were two new operators defined in terms of P, the momentum operator, and X, the position operator. A plus we called as creation operator, A minus is the annihilation operator, or step down operator is A minus, step up operator is A plus. Using these two operators, we defined the wave functions, the eigenfunctions of the harmonic oscillator. We said that if phi n is the eigenfunction of harmonic oscillator, the eigenvalue is given as where E n is in this way. We understood that, so here n would go from 0, 1, 2 and so on. So therefore the lowest allowed energy is half h bar omega, the next one is 3 half h bar omega, and so on and so forth. These are the different eigenvalues of harmonic oscillator problem that we obtained. The eigenfunctions phi n had a general formula which had a normalization constant a n, a Hermite polynomial expressed in the dimensionless coordinate rho, and this Hermite polynomial is the order of the Hermite polynomial is given by this index n here, and the third part is the Gaussian function e rho minus rho square by 2. If you remember, this rho is we defined this rho as the dimensionless coordinate, which is simply the multiplication of beta and x, where beta is defined as beta square is m omega divided by h bar, where m is the mass of the oscillator, omega is its angular frequency, and h bar is the Planck's constant divided by 2 pi. So this is the general formula of the harmonic oscillator eigenfunctions, and this is the general formula for the harmonic oscillator eigenvalues. We discussed in the last class as to how these wave functions appear, how the square of the wave function psi star psi, the probability density of this wave corresponding to these wave functions appear at different values of rho. One particular thing that we discussed in earlier class that I would like to remind you is that these functions, the phi n, have definite parity. That means that for a given value of n, either our eigenfunction is an even function or it is an odd function. But any eigenfunction of harmonic oscillator has a definite parity. So what are the advantages or disadvantages? What are the advantages of having this definite parity? Is that when we have if we have an even function, suppose we want to integrate an even function from minus infinite to plus infinite, and I have an even function here, I simply can write in this integral as 2 times the same function. If the function is even, I can write this. What is the change? Is the point that I am using here is that from minus infinite to plus infinite can be separated into 2 regions. One region from minus infinite to 0, the other region is from 0 to plus infinite. Since the function is an even function, so therefore the area under that curve, area under the curve of that function is same when I integrate from minus infinity to 0 as it should be from 0 to plus infinite. So, therefore, instead of writing from minus infinite to plus infinite, I am making it 2 times the integral where the limits are now 0 to plus infinite. This relation we used in previous classes. What if the function is, instead of being an even function, what if the function is odd? Suppose I have this integral where the function is now actually an odd function. So, here I can see that this limit is from minus infinite to plus infinite. I am writing down this as minus infinite to 0, the function is odd, plus another the same function from 0 to plus infinite I am integrating. So, in this case I have 2 integrals, from one is from minus infinite to 0, another is from 0 to plus infinite, but since the function is odd, so therefore, the value of the first term is going to be the negative of the value of the second term. Why is it so? Because we said that the function is an odd function. So, in that case, the total integration, when I integrate this function from minus infinite to infinite, I get the result as 0. But when it is an even function, I simply get twice the integration result of the integration from 0 to plus infinite. These two relations we would use to discuss some important properties. In particular, we are going to discuss now what are the expectation values of position operator and momentum operator. To remind you, when we say that we want to discuss the position operator, we simply write this, the expectation value of the position operator, we simply write this. What does this mean? This means if my function, if the system exists in one of these eigenfunctions of harmonic oscillator, I have to evaluate this integral. So, where phi n is one of the eigenfunctions of harmonic oscillator and phi n star is its complex conjugate. Now, the middle position here x is actually the position operator whose action is simply multiplication of this function by x. Now, we know that each eigenfunction of harmonic oscillator has a definite parity, either it is an even function or it is an odd function. Suppose we assume that this phi n happens to be an even function. If phi n is an even function, phi n star is also even function, because this is simply complex conjugate of the function, but we already have seen that the eigenfunctions of this harmonic oscillator problem that we obtained, they were all real eigenfunctions. So, therefore, phi n is essentially equal to phi n star. But in any case, since phi n is even, phi n star is also even, and what about x? X is an odd function. So, therefore, overall when I have these three functions I multiply, this is an even function, this is an odd function and this is an even function. Together I see that this is an odd function. Now, since this is an odd function and I am integrating this from minus infinite to plus infinite, I know when I do this integration for an odd function we just discussed, the result is going to be 0. So, what it tells me is that the expectation value of position operator for harmonic oscillator eigenfunctions is 0. What about the momentum operator? So, we want to obtain the expectation value corresponding to the momentum operator. The rule is same, we write down the following integral. So, we have phi n star, I am now writing down the operator form of the momentum operator. So, here again phi n star, they again have definite parity. If phi n is an even function, the first derivative of this function is going to be odd, and since phi n is even, phi n star is also going to be even. So, now phi n star is an even function, this term phi n is even, but differentiation of phi n with respect to x is going to give me an odd function if phi n is an even function. So, therefore, this is an even function and this is an odd function, and together I have an odd function. If I take the other case where phi n is, instead of being an even function, is an odd function, so its the first differentiation I would get as an even function. So, if phi n is odd, the d by dx of phi n is an even function, and since phi n is an odd function, phi n star is also an odd function. So, I have an odd function multiplied by an even function, together I have an odd function. So, whether phi n is an even function or phi n is an odd function, the value of this the function that we are integrating over here is going to be odd, and if the function is going to be odd, the result is also again going to be 0. So, we now what we in these two exercises, what we did is that we could obtain the expectation value or the average value of the position operator and the momentum operator of harmonic oscillator problem without actually calculating these integrals. How did we do this? We just used the beautiful properties of the harmonic oscillator eigenfunctions, the property corresponding to the fact that they have definite parity, they are either even function or odd function. In the same way, we can also in the same way we also can try to obtain the expectation value of potential energy operator, expectation value of the kinetic energy operator. I would not do this, but I would encourage you to carry out these exercises to obtain to gain information about what are the expectation value of this potential energy or kinetic energy operator of harmonic oscillator problem eigenfunctions. We would continue our discussion. And another point, what is known as the classical turning point. If you remember, before we discussed the quantum mechanical harmonic oscillator, we briefly discussed about the classical harmonic oscillator. We saw for a classical harmonic oscillator, it is in kinetic energy and potential energy, where sine square or cosine square functions which were oscillating in nature, but the total energy E is equal to k plus v. So, the kinetic energy and potential energy were keep on changing its the energy was keep on changing from one form to another form, or kinetic energy to potential energy and vice versa, while keeping the total energy of the system constant. What we to write this down, we saw that we had in the for a classical harmonic oscillator, we had this relation. The total energy was is equal to the sum of kinetic energy and potential energy. Since we know the kinetic energy is always going to be a positive quantity, kinetic energy is going to be greater than or equal to 0. So, therefore, we have this relation that the total energy is going to be greater than or equal to the potential energy of the harmonic oscillator. At most it can become equal, at the least it can be the total energy can become equal, otherwise in all other cases the potential energy is always going to be lower than the total energy. What does this mean? This simply means that if this is my harmonic oscillator potential, the potential energy is shown here. Suppose I choose that this is the total energy of my system, this is my total energy. Now, this when the harmonic oscillator has this kind of energy available. So, this x in the x axis I have the I am plotting x or the dimensionless coordinate r rho. One of the two I am plotting. So, this is essentially the dimension of the problem. So, if the system has got this energy E, it has got two components, the kinetic energy and the potential energy. What are the potential energies? Depending on the value of x or rho, my potential energy keeps on changing. So, if my x is here, there is the potential energy is 0, and therefore, all the energy that the system has is is kinetic energy. As I go along, as I move along this displacement axis, I have, for example, if I choose here, this is my potential, if this is my x, this is my potential energy, and this is my potential energy, and this amount is my kinetic energy. Similarly, if I choose this as my x, the displacement, this much becomes the potential energy, and this is the kinetic energy. In this way, I can go along this displacement axis and see what is the contribution of kinetic energy and what is the contribution of potential energy to the total energy. If you notice, if I reach this point, that means this value in the displacement axis, at this point the potential energy becomes equal to the total energy. And in this case, what happens to the kinetic energy? That means if my the displacement is up at here, this value of displacement, all the energy of the system is potential energy. So therefore, the kinetic energy is 0. So when the kinetic energy is 0, so at this position the oscillator actually oscillates back. So therefore, instead of going further in this displacement axis, the oscillator comes back, comes in the reverse direction. So I see a fall in the potential energy, and then again I would increase the potential energy along this direction until I reach this point again. Again at this point also my total energy is potential energy. So therefore, the kinetic energy is 0. So these two regions, these 2 points are called the turning points. This is one turning point, this is another turning point. So classical harmonic oscillator is allowed to move to show displacement between this and this turning point. Beyond these turning points, these are all forbidden region. For a classical harmonic oscillator, all these regions are forbidden. Why? Because if the system has to go up to this displacement up to this point, its potential energy becomes greater than the total energy and the kinetic energy becomes negative, which is absurd. So therefore, the classical harmonic oscillator is confined within the 2 turning points. Now we'll take this discussion and use the knowledge that we have obtained for the harmonic oscillator problem that we did solved from quantum mechanics. So the solution that we have now, we saw, okay, so to obtain some idea about the relation between kinetic energy and potential energy, we saw that the energy of the system should be always greater than, total energy should be greater than the potential energy. And for a quantum mechanical harmonic oscillator, the total energy we obtain is as h bar omega n plus half, and the potential energy was half k x square, where k is the force constant. If you remember, we defined k as we defined omega as k divided by m, and therefore k is m omega square. So therefore, h bar omega into n plus half is half. Instead of k, I now write m omega square. So if I simplify, I keep this n plus half in this side and bring h bar omega to so this 2 I can bring to the left side. So I have 2n plus 1 greater than or equal to m omega divided by h bar x square. And if you remember, this m omega by h bar is my beta square. So therefore, I can write this beta square x square, and since I have defined beta x as rho, so this becomes rho square. So rho square is less than equal to 2n plus 1, and therefore, rho should be less than equal to 2n plus 1 square root and plus minus. So, what do I get here? I get here the value of rho, which is the dimensionless coordinate. The value of rho, what are the allowed values of rho for a classical oscillator? For a classical oscillator, in this case, to make sure that the potential energy is less than the total energy, my rho should be within these values. So, these are the plus and minus 2n plus 1 are the two turning points. This is what we define as the classical turning points and use the expression for the quantum mechanical harmonic oscillator. Now, for n equals 0, the lowest value, for when I put n equals 0, so this simply means for n equals 0, the rho, the turning point should be simply n is 0 here. So, therefore, the turning points are plus 1 or minus 1. So, for if this is now my rho axis, so this is 0 and this is plus 1 and minus 1. So, these are the two turning points for the lowest eigenfunction of harmonic oscillator. What this means? This means that if my harmonic oscillator, if it were a classical harmonic oscillator, it would actually be confined between minus 1 to plus 1. So, these are the classically allowed region, and these are the forbidden regions, because if the system approaches the region beyond these values of rho, in that case the potential energy will become greater than the total energy of the system. So, therefore, they are forbidden region. But interestingly, what happens is that, so in this case what we find is that rho equals plus and minus 1 is are the turning points. So, let us write now what was the functional form of the lowest eigenfunction of the harmonic oscillator. So, this was 1 over pi, this was the normalization constant, e to the power minus rho square by 2. The probability density was so if I find out what is the probability density at rho equals 1, either rho is plus or minus 1, then you would see that and we know this quantity is not equal to 0, rather it has a finite value. What does this mean? This means that at the turning point, at the classical turning point, rho equals plus 1 or rho equals minus 1, the probability density of the harmonic oscillator is not 0. That means, I have a finite probability to find the system at the classical turning point. That still does not violate anything, but if you do this calculation for any value rho equals suppose 1.2 or 1.3, then also you would see that this probability density is non-zero. So, that means, if the probability density is non-zero beyond rho equals plus 1 or minus 1 for the lowest eigenfunction, that means what? It simply means that in case of the quantum mechanical harmonic oscillator, my system can actually go beyond the classical turning points. So, the regions that were forbidden for a classical harmonic oscillator is now accessible for my quantum mechanical oscillator. So, how does the system achieve this? So, these are the two turning points. If I plot the wave function or the square of it, this should look something like this. At rho equals 0, the function has a maximum, and then it decays like a Gaussian function with a bell shaped function. So, you see that at the turning point, instead of the wave function having amplitude 0, it actually has a finite amplitude. So, therefore, the probability of finding the system at turning point is non-zero, and what is more interesting is that even beyond this classical turning point, I have finite probability of finding this system. So, that means what has happened is that we express this observation as something called tunneling, which is a purely quantum mechanical phenomenon. Here it says that the potential energy, the system explores the region beyond the classical turning point, and that happens by the virtue of tunneling. If you remember the story in the particle in one dimensional box, we had the potential which was something like this. At the boundary, the potential energy was simply becoming V equals infinite, V equals infinite, and within the box the V equals 0. So, at this point, at the boundary, there was a sudden rise in the potential energy. So, therefore, this was a very hard potential. If you remember the solution of those problems, the particle in a one dimensional box, at the two end of this box, the wave function and its probability was becoming 0. But in case of harmonic oscillator, that is not the case. In case of harmonic oscillator, the potential is not a discontinuous function, not a hard potential, rather it is a soft potential. That means it continuously varies along the potential energy is a continuously varying function along displacement, and because of this soft nature of this potential, that we see this quantum mechanical tunneling. Quantum mechanical tunneling is an important property of this harmonic oscillator problem that we discussed today. The remaining part of the harmonic oscillator problem will take on in the next class. Thank you for your attention.